Morning. Yesterday we finished reviewing the vector algebra, and today we will continue from where we stopped with respect to aquifer properties. We looked at the storage properties of aquifers, where we deliberated on some of those storage properties: specific yield, porosity, specific retention, storativity, and specific storage. So now we'll move on to the next phase, which is the transmission properties. And under this, we will discuss basically three things, or two things: hydraulic conductivity or permeability, and transmissivity or transmissibility. And then there are other properties which we will discuss vis-a-vis the transmission properties, which are the isotropy and homogeneity. Okay? So this morning, let me push this. Because because I need this space. This morning we will look at Darcy's law. Darcy's law forms the basis of the flow of fluid in porous media. It is basically a motion equation, and I'm pretty sure you must have done it before. You must have done it in soil mechanics, and then hydrology, groundwater hydrology. It is the same thing that we are going to look at again, but now with some we'll start from the very beginning, the way you know it, and then, given that this is an advanced class, an MSc class, we will see how else can we represent the Darcy's law in view of what we have discussed before with respect to vector algebra, and also in view of the fact that quantities are either scalars and vectors. And then we will see what else can we do, because it forms the basis of groundwater modeling. At the same time, you must have done, I think there is hydraulics 2, right? Is there hydraulics 2? There's hydraulics 2. Okay. So I think in hydraulics 2, you must have considered Euler's equation, Navier-Stokes equation. Haven't you done that in hydraulics 2? Euler's equation, Navier-Stokes equation. Did you hear Navier-Stokes equation? Have you heard of this before? Oh. Haven't you done hydraulics too? Huh? Huh? You have done it. And you never discussed anything about Navier-Stokes equation and Euler's equation. You touched Euler's equation. But this one, no. And you have never come across it in your studies of hydraulics too. Huh? You had? Okay. Okay, then Whether you have heard this or not, what about momentum equation? Have you heard about momentum equation? Where? Not momentum. Not momentum.
Not momentum.
Yeah. I say momentum equation. Not the momentum you know from Newton's second law of motion, that the rate of change of momentum with time is it constant or what is it? Sorry, the force is proportional to the rate of change of momentum, isn't it? And then there you define momentum as mass times velocity, or change in velocity, right? Is that the momentum you are talking about?
Yes, sir.
Okay, I'm not referring to this one. Although even that one is derived from the from the basic principle of the definition of momentum, but it is called momentum equation. Have you heard about that one? Where? Rain. Good. Rain 201, rain 301, you all have even derived probably the momentum equation. Okay? So when expanded in 3D, the Navier-Stokes equation is the momentum equation for Newtonian fluid. Okay? The Navier-Stokes equation is the momentum equation for Newtonian fluid. And then that takes us to something else. What is Newtonian fluid? No idea. Yes, my friend over there. What is a Newtonian fluid? Yes. You also have no idea? Huh? And then, huh? By no idea, are you saying that you have never heard the word Newtonian fluid, or probably you did it before, but due to passage of time you forgot now, or what? Please don't tell me that this is the first time you're hearing this. Huh? What about you? What is happening? This is water resources class, right? I mean, those specializing in hydraulics and hydrology.
The separate words are familiar. Newton,
What?
the compound word.
That is unfamiliar.
It's very unfamiliar.
Newtonian fluids are fluids that has zero viscosity.
Zero viscosity?
They don't have viscosity.
Hmm?
Something like that.
So you had the word before or what?
Yes.
Okay, well, let's start from there.
Rain 201 also.
Rain 201 also.
Yes, sir.
So did you take different rain 201 with him?
I have not done REM 201. I started with REM 301 here.
Was rain 301? Why?
I entered as special
As
applicant.
as what?
I started trainer level here
Yeah, but why did you do your 100 level and 200 level?
at Polytechnic.
Yeah, but you must have done fluid mechanics there.
We have
I'm
done
sure.
fluid mechanics.
What is Newton's law of viscosity? Because that will now, these are things that ordinarily I will just pass by, but fortunately, every time I try to find out about some basis, I realize as if this is the first time you are hearing these things, and this is an MSc class, not undergraduate class. So I become really surprised that what has happened to, what have you done in your undergrad? And these are things that you must understand before we move on. There are things that ordinarily I will just come, okay, momentum equation, this, I will just pass by. But from my experience, that's why no matter how simple something is, I will have to make sure that you really know it. I will not just assume that, no, this you must have done it and just continue. Based on that assumption, no. Newton's law of viscosity.
Shear stress of a fluid is directly proportional to, I think, hydraulic gradient. I can make it.
What?
Shear stress is directly proportional to hydraulic gradient. Tau is equals to yes, mu du dy.
The velocity gradient. So shear stress is proportional to the velocity gradient. And what do you call those fluids that obey this law? Haven't you seen this equation before? The rest of you? In fluid mechanics, REN 301. Haven't you come across this equation before?
We have.
But some are, their facial expression is telling me this is the first time I'm looking at this equation. Like this man.
No. That's not my facial expression.
So what is your facial expression saying?
I'm just picturing myself, forgetting all this.
I always tell you, these are some basic things that you, due to passage of time, maybe you may forget, but when somebody mentions it, at least your brain should, send some signal that, I have had this thing before, but I may not be able to say exactly what it is now. Did you get my point? But you have to move even a step further, probably to have some idea. That is very important, most especially you that are specializing in water resources. Some of you here are teachers, isn't it? Are lecturers. Or some of you will be one day. Because you don't just go for postgraduate studies just for the sake of having MSc, isn't it? Some are lecturers, some are would-be lecturers. So you need to understand all these basics so that you teach your students. Not even teach your students, in your various thesis, MSc thesis, you will need all these basics to understand what you are doing. If not, a simple question will put you off track. You will come with your thesis and someone, sitting and listening at what you are saying will just ask you some basic thing based on your work, and you will look empty-headed. And that will terribly mark you down. Imagine someone doing his thesis on fluid mechanics, and then he was asked, okay, what is Newton's law of viscosity? He says, no, I don't know. What are Newtonian fluids? He said, I have no idea what that is. Just imagine someone during his defense. It means he is gone. He doesn't know anything. Because thesis is not something that, I'll just go and put this major this, write down, okay, this is the head, this is that, come and present table, and then just go on. No. You must have a deeper understanding and the connection between what you are doing and the basic principles. Because those basic principles are what constitute all the advanced formulations that you can ever have. So if anybody asks you about the basic principles and realize that you don't know anything about them, then it means it's just like a black box. In, out, what is happening inside, you don't know. And that is not how engineers are. Okay? So, I think as a word of advice, probably you all have your REN 201 notes, REN 301, and REN 503 notes. If I were you, I would go back, get my notes, go over them. Because now you are not studying for exams. Did you get my point? You are studying to refresh yourself about some of these terms so that you will not be found wanting again. Did you get my point? So you go back, take those courses, your lecture notes, although some of you will tell me, ever since I graduated, all my lecture notes have been dumped in the sea. Meaning I don't have any lecture note again. To review all of them, this groundwater hydrology, we move everywhere in mathematics, fluid mechanics, and what have you. And that is how knowledge is. It is not an island. It cannot stand alone. It must be supported, by various pillars here and there. It cannot stand just alone. It cannot be an island. Okay? So, Newtonian fluids are those that obey the Newton's law of viscosity. And the Newton's law of viscosity states that the shearing stress across a boundary is proportional to the velocity gradient. And even here, there are some calculations here, which I suppose you must have done in 301. But you have all forgotten that now. So, why I even asked about this Newtonian fluid, because I was just explaining the Navier-Stokes equation, isn't it? I said it is the momentum equation for Newtonian fluid. But then, like I said, nowadays I don't assume that no matter how simple something appears to me, I don't assume that you are all, the concept is up to date in your mind. So that's why I say, okay, I mentioned Newtonian fluid. So let me find out. Do you remember what Newtonian fluid is? Okay. So water is a Newtonian fluid, okay? And the Navier-Stokes equation is the momentum equation for Newtonian fluids. Now, going down to the Darcy's law. The Darcy's law is a particular or special case of the Navier-Stokes equation. It is a compact, a special case of the Navier-Stokes equation. Okay? But unfortunately, most of you say that you didn't come across the Navier-Stokes equation at all. But at least you came across the momentum equation. Okay? That you must have come across. Okay? But then, now, going back, let me now sit down to the Darcy's law. If someone tells me he forgets what Darcy's law is, then that person is going to be withdrawn from this course. So, let's start with Darcy's law. Can you tell me what Darcy's law is? Yes. Rate of flow of fluids through a porous media is directly proportional to the area normal to the direction of flow. Okay. Do you agree with him?
Yes, sir. The velocity of the flow is directly proportional
To the hydraulic gradient. Can you give us any mathematical expression of the Darcy's law? Any mathematical expression? Like I said, you must have done Darcy in soil mechanics, CVN 321, groundwater hydrology, REM 503. These are the two, at least in these two courses, at least. Any mathematical expression?
V equals to Ki.
V equals Ki. Okay. All right. So, Darcy was a French engineer and works with a treatment plant, and was experimenting with the filter media, sand, and then he came across these observations as explained by, what's your name? Awal. Let me see if I can get your names before we finish this course. So he observed that the rate of flow of liquid through the porous media is directly proportional to the hydraulic gradient, and it's called the first law of hydrogeology. The basic form is that the average linear velocity V or more, because this is not V, it's more, isn't it? Pronounced more, equals minus K over N dH by dL. And the full form in 3D is minus k dot del H. So now we will start applying our vector algebra, which we have learned. Okay? You can see dot, right? Dot product. And you can see del. That inverted delta is called or pronounced del or nabla or gradient. Okay? Gradient of H. And did I explain that before about del? I didn't explain anything about del?
Yes.
Okay. Del is a gradient operator. It's a vector, by the way. It is a vector. So it is in bold, okay? Although also you have seen the K being underlined. Okay? It has a meaning. And the meaning is that it is a second rank tensor. Where we are going to explain that. But now let me start with del. Del is a gradient operator that converts scalar to vector. Because del by definition is del by del x, I, plus del by del y, j, plus del by del z, k. This is the definition of del. So you can see it's a vector, right? If you have a scalar that you want to know its magnitude or the direction towards of greatest ascent, the direction in which it has its greatest rate of increase, then you now use the del operator. Okay? Because head is it scalar or vector? Pressure head, is it scalar or vector? Yeah. It's a scalar, right? But when operated using the del operator, it becomes vector. Because now what do you have? When you have del H, it becomes what? Del H by del x by del xi plus del H by del yj plus del H by del zk. So it becomes a vector now. Though this is now called the gradient operator or the gradient, okay, which gives the direction of greatest rate of increase of the head in this case. Are you following? So now you have a dot product, and this is a second rank tensor. That's the hydraulic conductivity. It is a second rank tensor. You must have done mechanics of materials, CVN 305. You did stress tensor, isn't it? CVN 305, right? Mechanics of materials. Right?
Some did.
What?
Some did.
Some did.
Yes.
Is it expunged out of the curriculum now?
Yes.
Okay, are you sure? It's still there. So all of you have done it. At least those that have passed through ABU, right?
Yes.
Or through civil or water resources, isn't it?
Yes.
Because some of you might have passed maybe through chemical and what have you, or not even product of this university. But even if you are not a product of this university, you must have probably studied civil engineering somewhere, and this shouldn't be something new. Okay? You must have done stress tensor, isn't it?
Yes.
Stress tensor. Okay. I will go and explain that later. Now, that's the first law of, we are going to break down the components of the Darcy's law and explain from the elementary level up to the advanced level. Okay? Yeah.
You mean that the Darcy law is one clarification of hydrology?
Yeah, the hydrogeology. Yeah, hydrogeology. It's called first law of hydrogeology. Just like you have first law of thermodynamics, second law of thermodynamics. So hydrogeology, sometimes they call it the first law of hydrogeology. And the second law now is the flow equation, which we are also going to deliberate later on. Okay? In 1D, steady state, you have d squared h by dx squared equals 0. And this is generally, or the compact form of what is called the Laplace equation. Have you heard about the Laplace equation before? Oh, so that one you know. So how do you represent the Laplace equation using the del operator? The Laplace equation is given as del squared h equals 0. This is the Laplace equation. Not Laplace transform. Laplace transform is different. Have you heard of the Laplace equation? Don't confuse it with the Laplace transform. Are you following? Laplace transform is different from Laplace equation. Laplace equation forms the basis of groundwater flow. For steady state, you have it expressed this way. And now with this, I'm sure you can expand this one. Because this is in 3D, right? This is for 1D, steady state. For the unsteady state, the transient state, you have it expressed. You can see del dot k dot del h. All these are vector operations, isn't it?
Yes.
Okay? And later on, for steady state, you have del h by, sorry, for unsteady state, you have del h by del t to show that the head varies with time as well, in addition to spatial variation. Okay? This, we will go to this equation later on. Okay? But now we are here. Because it is from here that you graduate into this, and then you graduate into that. Okay? So later on, we are going to expatiate on all of these equations. But currently, we are here. Okay? Now, as Awal has mentioned, Darcy investigated groundwater flow under controlled conditions and realized that the flow through the porous media is directly proportional to the change in head, the difference in head. As the flow is flowing in this direction, you can see the direction, the head here is higher than the head here, and there is difference in head. So the more the difference in head, the higher the flow. And by the way, why is the head, why is H2 lower than H1? Can you tell me? Why is H2 lower than H1 from this figure? What? What? The head? So why does it decrease along the direction of flow? Why is that so? Why is it not constant? Or why is it not increasing? Can you tell me why that is? I agree with your proposition that it decreases along the direction of flow, but why? Why won't it remain constant or even increase? No, you have answered my question today. So I will point at someone again. You know, instead of like having one person to be answering all the questions, it's better each and every one of you participate in the question and answer session. Isn't it? Yes. Can you give me any insight? Can you bail him out? He said something which is correct. Yeah, it decreases in the direction of flow. But why? No. Yes. What's your name? Musa. Why? Hmm?
As a result of the rate at which groundwater is being rising up. The rate at which bores are being done.
The rate at which
Water is being removed from the water.
water is being removed from.
Water.
No, this is just flow of water. And don't forget, this is tilted. So it's flowing under gravity. So here it appears as if it were horizontal. It's tilted. Okay, so that is, it's tilted because it's flowing under gravity. What's your name? Muhammad. So Any insight into this? Why the head is decreasing in the direction of flow? No, not you. Or do you have an answer to it now? Eh? Pardon? Yeah, I agree it decreases, but why? I'm asking why? Why? What?
Because the pressure is reducing, so the constant is.
What?
The pressure is reduced and the constant increases.
And the
The K is increasing, so it's causing the pressure.
the K increases? No. Abdullah, why do we have decrease in head in the direction of flow?
In first head, the pressure is higher, so as it moves along the x-axis, it reduces.
Why? I want the whys, not just the observation. Yeah, I agree. It reduces, and definitely it's going to reduce. But I'm asking why. What? Oh.
So I think maybe the velocity contributes to the reduction of the pressure. As it moves, the pressure reduces. If it were stationary in one place.
Okay, come back, please. Sorry, come back again. Let me listen.
As a result of flow, there's movement, so the velocity results into the reduction of pressure.
You see, if I so wish, I can finish this course probably, let's say, in 5 lectures. But at the end, probably the outcome, the real understanding of the concept will not be there. Ordinarily, I shouldn't be taking so much time asking you all this. If not for the fact that I realize there are a lot of things probably that either you forgot or the concept is not clear. And once that is not clear, you cannot model correctly. Like I told you ab initio, that modeling entails studying the system thoroughly. And modeling, like I told you, although we are going to explain that later, you have various, approaches to modeling. You have numerical modeling, statistical modeling, and what have you. Numerical modeling is the most difficult one. But once you understand numerical modeling, then any other modeling technique will be easier for you. And that's why this one is numerical modeling, which is having to do with governing equations, partial differential equations. Because in this case, for numerical modeling, you have to understand the system in total. Unlike in others, because like statistical modeling, sometimes it's not even necessary that you must have the knowledge of the processes very well. You can have your result and just try to find some relationship between the variables, this and that. But for numerical modeling, no. Every parameter, you have to know it and understand it without any ambiguity. And that's why no matter how small a thing is, or a process is, or whatever, I will ask. If you give me the correct answer, then I move on. But if you don't give me the correct answer, then even if it means spending the next hour or the whole lecture time asking and trying to explain that, I will do that. So that at the end of it all, at least you will have something to take home. At the end of the course, you will feel that, okay, I have gained 1 or 2 things here and there, which is the most important thing. So now, go ahead. Go ahead and tell me why. Because I will not proceed until I have good explanation. And this is water resources class, hydraulics and hydrology, not environmental engineering class. Even those in environmental engineering, it will not be an excuse for them not to tell me why the head reduces in the direction of flow, let alone the hydraulic specialists. Yes. No, he's trying to explain. Let me hear him out if he can give me the reason, and then we can move on. Yes, go ahead.
At H1, permit me to say that it's stationary. So as a result, the head is high, but it moves as it flows. The flow in the water
Have you done around 501?
It's due to losses, sir.
Due to?
Losses.
Because I mentioned around 501, so that's the first thing that came to your mind.
Of it, but I'm not sure. I just told you something about it.
What?
I've been thinking about it, but I'm not so sure whether that's the cause.
You are still not sure?
I'm still not sure, but I think it's due to losses. It's due to losses. Because I remember the other class, you draw something talking about why the water is not go, which is due to some major lines, the losses along the connection and losses. So I think this one is also due to losses.
I think there are two factors that are contributing. As the fluid is moving along the medium, there must be frictional resistance first by the grains of the medium. Then some portion of the fluids will be retained in the voids along the medium. These are the two contributing factors.
So you are still saying the same, virtually the same thing as due to losses? More or less?
Okay.
Of course. Now everyone is saying, of course. Of course.
Why the thought of losses didn't come immediately was I was thinking this flow is actually underground. So
You did run 501 pipe flow. But as it is flowing, there are losses, isn't it? You did this even in 301. All the types of losses due to bends, due to this. As water is flowing, it is losing head. Due to, you have minor losses and major losses. The major loss is due to frictional resistance. The minor loss is due to bends, due to this, due to change in the cross-sectional area and what have you. Oh, were you given just handout which you memorize and just pass the exams or what? I mean, these are some basic understanding that I just don't know why you are missing it. Why is the, yes, it will definitely reduce, which you were just reiterating before. But why? Due to losses. As it is flowing, the head is losing, the energy is being lost. Due to what? Frictional resistance. And that's it. Then I would have moved on. And here I am spending 20 minutes hammering on frictional losses again. Oh, haven't you taken your breakfast this morning? Huh?
Yes.
Huh?
Yes, sir.
You did?
No, I didn't.
Please, when coming to my class from now henceforth, make sure you take a balanced diet. And you know the most important meal of the day is breakfast. So if you so wish, fill your stomach to the brim, up to up to here, but don't come and vomit in the class, okay? But make sure you will be late. Why will you? It's a matter of planning. At 6 you get up, cook your food or get your food. If you are married, if you are a bachelor or whatever it is, and then take it, then come to class. So that your brain will have enough food to be thinking, in retrospect. Okay? These are some basic questions. Like I was at the undergraduate seminar. They did a lot of geophysical survey. But when you ask them simple things, they found layers. When they were asked to sketch the layers, and they will look as if you are speaking a language that they never had. When you ask them simple things, someone couldn't define an aquifer. He did geological investigation to determine the depths to groundwater. And when asked to define an aquifer, he couldn't. So these are things that are basis, isn't it? That no matter what, most especially, he was working in that area. Yet he couldn't define an aquifer. That is terrible. I can only imagine. I said, haven't you passed REN 503? Because even if you don't pass it, at least your project is in that area. So you must have done literature review. You must understand the aquifer properties, what is an aquifer, this and that. But you realize there is huge gap between what they are presenting and the knowledge base. And that is really terrible. And to be candid, something similar happened during some external defense that took place recently. External defense. You ask them basic things, simple things related to what they did. They cannot answer it. And that is indicting. That is indicting. Most especially, let's say, okay, you may have different areas that you want to work on for your thesis. every theory, every basic principles to do with that area, you should go and review it. You should not be found wanting. At least in that area of your space, of your, your project area or whatever it is. You shouldn't be found wanting on any basic idea. Because sometimes you may be thinking that, they will be asking you a lot of questions about, okay, how did I get this? How did I do? But then you will go up, but when the lecturers go down, that is when you will be taken off balance. You will be thinking of a lot of difficult questions to come your way. But when they ask you the simplest of questions, you will appear blank. And that is more indicting. And this happens if you just ignore these bases. This simple basis, Newton's law of viscosity, this and that. Because you come and you are presenting something on fluid. Someone can just ask you, what is Newtonian fluid? And you will do like this, Newtonian fluid. This is the first time I'm hearing it. And that will appear really indicting. As someone specializing in water resources, you don't even know what is a Newtonian fluid. Probably in your work there will be nothing applicable to Newtonian fluid, but they will like to know, okay, do you have the basic background? Because if the foundation is shaky, anything you build upon a shaky foundation, you of all persons should tell me that it will not be durable, isn't it? And these basic concepts are the basic foundation that you cannot do without them. You cannot do without them. I tell you, I was interviewing a professor. I asked him, what is Newtonian fluid? So don't think that the question, what is Newtonian fluid, at your level, no, this is, I'm too big for this question. You will never be too big for this question. Never. If I can ask a professor of civil engineering to tell me what is a Newtonian fluid, then if you think these basic questions, you are too big for them, think twice. Okay? Think twice. I remember someone went to an interview, he did engineering, probably with good class, and, he came with his certificates. Then he sat down. Then one of the panel members asked him, what law governs your sitting down on that chair? He looked left and right, up and down. What law? Which law governs your sitting down on that chair? Now, if I will ask you the same question now, what would you... let's now turn it around. Assuming I'm the interviewer and you're the interviewee. Who can now tell me that law? Newton's third law of motion. What does it say? Oh, so it means you'll pass that interview. But what I'm saying is that these basic principles, they are supposed to be imprinted. They are supposed to be magnetized in your brain. Of course, you may not be able to recall them exactly, but you should have an idea. And most especially you that are specializing in hydraulics and hydrology, you have no excuse whatsoever not to be able to remember any principle in hydraulics and hydrology. You have no excuse. Someone probably in environmental engineering, probably, because even that I'm not giving them excuses. No, but probably he may say, I did this long time and I'm not using it again, this and that. But you guys know there is no excuse, and no matter what you become, one day, one time, someone can ask you about these basic questions. What is Newtonian fluid? What is Newton's law of viscosity? And believe you me, if you are not able to answer correctly, that could be indicting. Okay? So, the bottom line is, take whatever you do as serious as anything. And now, it is still not too late, like I was telling you. It is still not too late to go back, because I'm sure you pass all these courses with flying colors, A's, B's, C's, isn't it? But now this is the time to really produce those, principles and whatever it is, you can still go back, pick up your notes, REN 201, REN 301, REN 401, REN 503, REN 501. Go over them, because now you are not anticipating any exams. So it is at your pleasure. You can relax, sit down, taking tea, taking this, while going over gently, so that your brain, is energized. Okay? Because this is just the beginning. I will keep on asking you every class about these basic aspects. I will keep on asking you every time you come to the class. Come prepared. We'll still be coming across all these basic, and that is because they affect us, isn't it? It is not just, I'm not asking these basic concepts just for asking sake, but because we need to understand them for us to appreciate what happens. Like I told you, they did probably a lot of geophysical investigation, but in a way they couldn't correlate what they did in the field with their knowledge of hydrology, with the practical application. So there is knowledge gap. Okay, maybe they want and take the reading. Okay, this is the resistivity, this is the depth, this is this. But in practical sense, okay, when I want to drill a borehole, is it to the confined aquifer or to the unconfined aquifer? Someone will do like this, and you will wonder exactly. I mean, is the same guy not a student under REN 503 or what? Or was he just giving handout which he just memorized to just go and write exams? And I'm sure no. But probably all those concepts he has forgot. He forgot about them, and now is the time to correlate between the theory and what you obtain, what you have seen in the field. Which is why we are engineers, not scientists, not just someone that will sit down and bring some mathematical formulation and just, no. We are applied scientists. And that's what give, the color to science, isn't it? Because science without engineers will just remain in book, just formulations, Laplace equation, this and that. But engineers will now take that Laplace equation and then use it to model a particular physical process. Okay? So let's move on. So now that we have understood, or we remembered why the head is reducing, and it will always be reducing. If you remember in my question, that's why I said, is it going to be reducing? Why is it not remaining constant or even increasing? Isn't it? But let me now ask you another question. Let's say you have a pipe flow. Could that be a scenario by which it will be increasing? It can increase, the head could increase?
If a pump is installed.
Good, okay. So now, I'm sure, you said you haven't taken breakfast, right? So if a pump is installed, I would have said, okay, what have you done in REN 501? Okay, so if a pump is installed, you see, these are simple questions, isn't it? But they are simple questions, yet they are important towards understanding, towards maybe for giving someone an impression about your real understanding of the basic principles. Because if you don't understand the basic principles, everything will just be mixed up in your brain. At the end, you won't come up with anything tangible. But if these basic principles are clearly understood, then that is the first step. Okay? Now, let's move on. He found out that the head decreases. The flow increases when the difference in head increases, isn't it? And then he realized that the shorter the length, the higher the flow, isn't it?
Yes.
And the longer it is, the less the flow rate. Okay? And then the higher the cross-sectional area of flow. This is the cross-sectional area of flow. The higher the cross-sectional area of flow, the greater the flow rate, isn't it? This is perpendicular to the flow. The cross-sectional area is perpendicular to the flow, and this is the volumetric flow rate. Now, from mathematics, we combine all this using the proportionality sign, and when we remove the proportionality sign, we introduce a constant called the hydraulic gradient. Okay? Called the hydraulic gradient. Okay? Although here, hydraulic conductivity. Now I would like to explain about gradient and hydraulic gradient. Is there a difference between gradient and hydraulic gradient? Okay, what is it? What is it? You shook your head, right? In the affirmative, that yes, there is difference. So tell me, what is the difference between gradient and hydraulic gradient? Yes, yes. Yes, can anybody help me out? What? Gradient and hydraulic gradient, how are they related? Gradient and hydraulic gradient? Anybody? Oh, yes.
Hydraulic gradient is just the slope of
The slope of the flow? Fluid?
water, while the gradient can be the slope of any.
You see, like I told you now, we will take each of the terms in the Darcy's law and explain in greater details. Okay? When we mention gradient, you know gradient in mathematics? Slope. dy by dx, right? This is gradient, which shows the direction of the greatest rate of increase of a particular quantity, isn't it? If I call it dh by dy, that is showing the direction of the greatest rate of increase, isn't it? Of the head. I can designate it using del H, right? Using the vector, isn't it? In 3D. Am I right? This is the gradient. The hydraulic gradient, which for now we will designate as J. Ordinarily we use I, isn't it? But then we will be confused when we use I. Why?
Because of the hydraulic gradient.
If you use what I?
Yes. It will confuse us with another term.
Of, what do you call it?
I don't know what you call it. Yeah, I don't know what they are. I don't know what they are. I don't know what they are. Oh.
Directions.
No, it's not direction.
Direction. Because of the direction. IGK
Hmm?
direction. Because of the IGK direction.
And what do you call them? Hmm?
Because of the Cartesian.
Just yesterday I was asking you to go and review all that we did in the vector algebra, right? What do you call them, the IJK? Cartesian unit vectors. Because we have this to be the direction of the x-axis, right? So if we use I as the head, then, because here we'll be expressing them in vector form. So that's why it's better we use J as the hydraulic gradient. Although J also, later on, when we'll start the solid transport, it will also, J is also another term for flux. The rate of flow of unit mass of, the mass of the contaminant per unit time per unit area is also represented as J, flux. But when we get there, we can now see what to do. But for now, we will use J to represent the hydraulic gradient. The hydraulic gradient is equal to, is negative of the gradient. This is the hydraulic gradient, which is negative of the gradient. Now, in practical terms, how can you now express the hydraulic gradient? I defined the gradient for you, right? So how can you now define the hydraulic gradient? And don't forget, there are vectors. The hydraulic gradient is a vector. Now, you see, thank God we just finished the vector algebra. So now you'll have to be thinking vectorially. In vector form, your way of thinking should also be in vector form. And the way you define things and express things. This is the gradient, and this is the hydraulic gradient. And I just defined the gradient. So what will be the hydraulic gradient now?
Minus xi minus
No, I mean, explain it to me. Yeah, as in, I explained the gradient, right? I explained what it means in terms of head, right? Now explain the hydraulic gradient using this relationship. You see, okay, here. This is the slope, right? Is decreasing. This is H1, H2. So this is the slope. And from mathematicians, they will tell you that this slope is negative, right? From coordinate geometry, Math 104, right? This slope is negative, okay? By definition, the gradient gives the direction of the greatest rate of increase. So on the other hand, hydraulic gradient, which is negative of the gradient, will be what?
The rate of decrease.
Huh?
The rate at
It will give the direction of the greatest rate of decrease in head, isn't it? What is exactly what is happening here? The head is decreasing, right? Now, treating them as vectors, let's talk about the directions. What about the directions? Like in this case, if it's this way, how will you represent the hydraulic gradient? Let's say just based on the direction of flow. If the direction of flow is this way, or let me make it inclined. The direction of flow, Q, isn't it? Is this way. Who can tell me the direction of the gradient? Because they are vectors, right? Oh, let me just say flow, because flow is a... Is it vector or scalar?
Flow.
Yeah, flow rate.
Is vector. Is vector.
Is vector?
And it has the reactivity of flow.
Is vector?
Yes.
Oh. Flow is vector? Volumetric flow rate is vector? It's a scalar quantity. It is a scalar quantity. So here, instead of using the flow rate, I will use the velocity, which is a vector quantity. So this is the direction of flow. And now, who can tell me the direction for the gradient? The gradient, same as the direction of flow. So the gradient del H, same. Then what about the direction of the hydraulic gradient? Opposite. You see, all these are vectors. So does this tally with our definition of gradient and hydraulic gradient? Now we are just starting the Darcy's law. We are just taking one aspect of Darcy's law, which is the hydraulic gradient. And even the hydraulic gradient, we are just like trying to understand exactly what is it. So basically we haven't started anything yet. Okay? This is just some preliminaries. But we need to get it right. Okay? So, is that correct? Based on the definition of gradient and hydraulic gradient?
Yes, sir.
You will say yes because that is, you suggested this answer. So, let others judge you. Is that correct?
Yes.
Yes.
Mathematically, yes, correct.
Okay, then what did we define gradient? Let's go by definition. What did we define gradient?
The greater increase of that,
The increase.
the direction and
Of the greatest increase, right? In this case, we are talking about head. So, this is the direction of the greatest increase in head.
it decreases.
Huh?
It decreases.
Then why are you telling me that, based on definition, that this is right? Okay, if it is wrong, how is it going to be?
Opposite.
Just that one is the H and one is J.
This is J, right? This is del H. And it's because they are vectors, they are related. This is minus this, isn't it? It's just like you have vector A. You remember we did vector A and minus vector A. If this is this vector A, then minus vector A will be that. The first slide in the vector review slide, isn't it? So, J is towards the direction of the greatest decrease in head. So it will have the same, it will be in the same direction with the velocity. Okay? While gradient will be up because it is increasing this way. Are you following? And that is very important because it has significance. Now, we are treating them as vectors and scalars and what have you. So direction is very important now. And in fact, it's something that we are also going to be finding. Okay? Magnitude and direction and what have you, which we did in vectors. Okay? So, I will come back to the hydraulic gradient later on. But for now, I think I can move on to something else. Let me move on to the hydraulic conductivity. Okay, K, which is the constant of the proportionality constant, the hydraulic conductivity. But before I do that, let me give you some few minutes to take some break. Okay? Let's take some break, and then when we come back, we will move on to the, but I hope the concept is clear. You now understand the difference between hydraulic conductivity and, hydraulic gradient and gradient, and why we have the negative sign. Because the gradient is always negative. The slope, the gradient is always negative because it's towards the direction of decrease in head. So the gradient will be negative, isn't it? It is always negative. And then the hydraulic gradient is minus the gradient. Is that clear? That point has to be made clear from the word go. Because in some of the expressions, you will see them writing the minus sign, and in others, no minus sign. When we use the hydraulic gradient to represent the Darcy's law, let's say Q equal K A J. No minus sign, because J is minus del H, isn't it? So there will be no minus sign here. While if we use the gradient to represent, okay, in the Darcy's law, then the minus sign has to come out. Is that clear? So that you don't get confused when you read text and you realize in this equation, no minus sign. So the author has made a mistake here. No. Open your eyes and look at what are they using. This is minus because here we use gradient. This is minus because here we use gradient. But if we use the hydraulic gradient, then the minus sign will go. Is that clear? Okay. So, back to business. I hope we have refreshed. All right. I was explaining the hydraulic gradient, right? And I said it's a vector quantity. And we mentioned that the volumetric flow rate is not a vector quantity. Okay? It is a scalar quantity. Now, yes, sir.
Sorry for running back.
Okay, go.
Volumetric flow rate is scalar.
Yeah.
Can you please make it more
Pardon?
elaborate?
Make it.
And explain why it is scalar.
Why won't it be scalar? It's a scalar quantity. It has no direction. I'll elaborate more. Don't worry. We are taking each of the terms, isn't it, and explaining now. But flow rate is a scalar. It's a scalar quantity. It's a scalar quantity. It's a scalar quantity. It is a scalar quantity. I'll expatiate more on that, okay? For now, let's move on to... I said you can remember something called stress tensor, isn't it? Stress tensor. CVM 305. Mechanics of... I think now... But before explaining about stress tensor, now let's talk about isotropic or isotropy and homogeneity first. Like I told you, we'll still be going back to basis, isn't it? Soil mechanics, geotech. So tell me, what is homogeneity as it affects porous media? What do we mean by homogeneity? Go ahead. It's just uniform. I say explain. Discuss. Okay. Discuss the meaning of homogeneity in respect or with respect to porous media. Yes? Okay.
When the media is uniform, take for example, say soil particles, that media they are constituted. I would say the grain size are uniform all through.
So that's what is meant by homogeneity.
So as a result of that, flow of fluid.
But can you find a porous media that has uniform grains?
No.
In practice? Yeah, synthetic porous media, yes, will have probably uniform grains. But real porous media to have uniform grains? Or what will you say in terms of the properties of the porous media? How can you define homogeneity in terms of the properties of the porous media? Or specifically, here we are talking about aquifer properties, right? So how will you explain porous media in terms of aquifer properties? We have considered many before, and we are still considering some now, isn't it? So how will you explain that? The meaning of homogeneity. Yes? Anybody? Yes. Let me start pointing now, since nobody is willing to volunteer. You, yeah. What's your name? Abdul Hakim, okay. Tell me. Uniform all through. No medium is uniform. What do you mean by uniform? In terms of the aquifer properties? What? What do you mean by quality? Yes? It's the same. What?
I'm trying to maybe that's what.
Okay. All right. Yes? Missivity, transmissivity.
Uniform throughout the aquifer.
It's uniform. So if you have this is the water table. Class, you may need to get me another black pen. And then you have probably confined aquifer. So the value of transmissivity is the same throughout. I mean, at this point it is T, at that point it is T, at every point it is T. Is he right? What about K? When we take, because now we are talking about hydraulic conductivity. What about K?
Yes, the same.
At every point is the same?
Having the same properties.
Yes, that is the meaning. But saying that the aquifer grains are uniform, that is far from it. It is the aquifer properties that are the same at every point within the porous media. Then we say the media is, the medium is homogeneous. Okay? And we discussed these aquifer properties. Like porosity is the same at every point. Okay? Then we say it is homogeneous. Now, but these are some of the basic assumptions. Otherwise, we say it is heterogeneous, isn't it? Heterogeneous. Most especially when you have different layers of soil, isn't it? When you have different layers of soil, definitely the properties of each layer with respect to, let's say, transmissivity, hydraulic conductivity, porosity, will change from one layer to the other. Because different layers will have different shapes of the grains, different, voids and what have you. And that will affect all these parameters. But that is even more or less an averaging system, because there is something called continuum. Although this is the first time probably I'm mentioning this in the class, but maybe later we may find time to explain this. Continuum, the continuum approach. You see, porous media is a very delicate and complex system. Okay? It's more complex than just, let's say, the pipe flow, open channel flow. Here you have scales. We may also explain what is meant by scales. You have different scales. You have the microscopic scale and the macroscopic scale. Here we are looking at flow at microscopic level through the void spaces, which is not regular, which is tortuous. You know what is tortuous? A tortuous path. Tortuous. Later we are going to explain tortuosity. There is a factor called tortuosity factor. But that will be probably when discussing about the solute transport. Because you have grains, of irregular shape. So the path taken is not just, straight. It is tortuous. Yeah, erratic. Exactly. It's based on where you have the interconnected void spaces. So this is at microscopic level. And flow in such system is really delicate, that if you are considering it at microscopic level, there is need for some averaging. Because in practice, you may not have homogeneous soil. Because all these values, they change from one point to the other. Because of the fact that the void spaces are not uniform. For that, the hydraulic conductivity changes, the porosity changes at every point within the porous media. But this change, when quantified, sometimes is not something reasonable. So for that reason, we approximate or we average. We average the value of some of these quantities and say it is uniform throughout the porous media. While in the actual sense, the porosity is NXY, NXYZ, it changes from one location to the other. But we are going to explain that in greater detail. And that's why for any modeling technique, the first thing you do is to lay down your assumptions. These assumptions are important because you are to state what are you overlooking. Most importantly, if you assume that the porous media is homogeneous, it means the value of K and what have you is a single value, although we are going to explain something else called isotropy. Okay, but at a point in space, let's say the porosity is a single value in space. Okay, and that means you will not consider porosity, let's say, having many values or dependent upon having spatial and temporal variations. And then the next term, which is isotropy. Let's discuss that. Isotropy. Can you tell me? Isotropy. Oh, let me write it down. So the continuum approach, we are averaging, we are taking a representative element volume and then assuming that the properties of the media is the same at all points within that, or it's a representative of the larger aquifer. That is the continuum approach, rather than looking at everything at microscopic level, because that will be more complex and more difficult, because as we are going to see later, these assumptions are meant to reduce some of the complexity in deriving the governing equation so that they will have solution, or what is called convergence. Because once your equation diverges, it means it will have no solution. And we want to have a governing equation that has solution. So with these assumptions, and the assumptions have to be reasonable. Okay? You don't just come up with assumption just because you just want to simplify and oversimplify your governing equation and say, no, this is a 1D model. Definitely, the accuracy will be far off the limit. Far off. Is that clear? But sometimes for the sake of teaching and what have you, you can start from simple to complex. Start from the 1D model and then see what can you introduce. Is the 2D model going to be adequate? Because sometimes even the 2D models are adequate in predicting certain responses. If it will be adequate within some error boundaries, then you go ahead with the 2D model. If it will not, then you go to the last one, which is the 3D model, which is the most complicated one. But all that we are saying is that we are trying to reproduce or simplify a particular physical phenomena using some sets of mathematical equations. We are reducing some processes, some physical processes taking place in nature by just representing them using some partial differential equations. So for that, we need to make sure that all the processes affecting the physical processes are captured, are well captured. If not, then the understanding of the system will be faulty. Because as we are going to see later, one of the importance of having models is not just for prediction. Prediction is one of the functions of modeling, to predict the value or the response. When you have an input, what will be the output? Prediction, isn't it? One of the importance of modeling is to understand the system in total. Not just for prediction, but it gives you an understanding of the system. And once you eliminate some of the important processes taking place or affecting that system, then your model will be deficient. And that is why we are taking our time to understand all the processes before going into the groundwater modeling proper. Although we have already started, but probably you say we haven't started seeing partial differential equations. But I'm sure now you have started seeing them. And you will keep on meeting them till the end. Okay? Now, isotropy. Isotropy. You see, now we define homogeneity in terms of the aquifer properties that we explained before, right? Now, isotropy. Go ahead. Is the condition?
Where the hydraulic property of an aquifer is the same in all directions.
Where the hydraulic property.
In all directions.
Did you check in your phone? No, tell me the truth. What?
I've checked earlier when you made mention of it.
Okay.
Homogeneity, heterogeneity, and actually
So you now quickly check. That is cheating. Although you know that definitely I'm going to ask. Okay. So he defined isotropy what?
As a condition where the hydronic property are the same, are equal in all directions.
Are equal in all directions. The aquifer properties when they are equal in all directions at a point. You see, don't get confused between homogeneity and isotropy. Homogeneity is saying that the aquifer properties are the same at every point, at any point within the aquifer. While isotropy is talking about a single point within that aquifer. That property, is it the same in all the directions, x, y, z? If it is, then you say the aquifer is isotropic. Okay? So, here we are considering hydraulic conductivity, K. Isn't it? At this point, is it the same in all the three directions, x, y, z? If it is the same, that is kx equal ky equal kz equal single value, a scalar value, then we say that the aquifer is isotropic. Otherwise, it is anisotropic. And you just add an, anisotropic. Okay? Now, with respect to hydraulic conductivity, we have different different rank tensors. You have zero rank tensor when it is just equal to a scalar, because hydraulic conductivity is a scalar. It is a scalar. Okay? Because now that we have done vectors, every quantity we mention, we need to know exactly whether it is a scalar, a tensor, a vector, because that will now tell us how to deal with it. Is that clear? So the hydraulic conductivity is a scalar. So if an aquifer is isotropic, so it will give us a single value, isn't it? And that is called zero rank tensor. Zero rank tensor. If it is a vector, like the Darcy velocity, which is given qxi plus qyj plus qzk. It has three values, isn't it? Three values. We call it first rank tensor. First rank tensor. If it is let me just cover it here. Oh, because I want to use the board. Okay. All right. If it has 9 values, then we call it second rank tensor. Okay. How do we represent a second rank tensor? Let me reproduce something you already know before. Okay, I think this one. Okay. All right. So if I have my right hand rule for the coordinate axis, this is y, x, z. Okay? I'm still referring to the hydraulic conductivity, which is a second rank tensor. And that's why we write it in bold, because now a vector, we will write it bold italicized. A tensor will be bold underlined, will double underline depending on the rank. Hydraulic conductivity is a second rank tensor. Okay, so, pardon?
You say hydraulic conductivity is a scalar?
Yes. No, I am differentiating the representation of vector and tensor. Vector will be bold, italicized. Tensor will be bold only. So when you see it bold, it doesn't mean here, in this case, it will be bold but not italicized. Is that clear? It will be underlined, depending on the rank. This is a second rank tensor. So you have 2 lines beneath. Okay? When you come to this phase, When you come to this phase, now this is the y-axis, so you have k, y, y. This is k, y, x. This is k, y, z. This is the z-axis, you have k, z, z, k, z, y, k, z, x. This is the y-axis, x-axis, you have k, x, x, k, x, y, k, x, z. These are the components of the hydraulic conductivity, 9 in number. Because this, you have the same thing repeated on the other side. This, the same thing repeated, like that. So it has 9 components. Hence, it's represented using matrix. Kij in subscript form or indicial form will now be equal to, it will be kxx, kxy, kxz, right? kyx, yy, yz, zx, zy. This is the matrix form. Okay? These are called the principal directions. Okay? These are called the principal directions. When the principal directions are aligned with the Cartesian, these are the principal directions. When they are aligned with the Cartesian coordinate system, in that case, all the cross terms, these are the cross terms, right? All the cross terms become 0. Because if they are aligned, you will only have this, isn't it? It will have no component here and there, isn't it? The same thing with this one. It will have no component here and there. Because all these are orthogonal, 90 degrees separating the axis, right? So for principal, when the principal directions are aligned with the coordinate direction, with the coordinate axis, which is this one, then all the principal, cross terms become 0. Hence, you will be left with only 3 values, kxx, kyy, and kzz. At the same time, the hydraulic conductivity tensor is symmetric. It is symmetric. By that, it means kzy is equal to kyz. And this will leave us with, instead of 9 terms, in a situation whereby the principal directions are not aligned, we'll be left with only 6 terms instead of 9. Because kxy will be equal to this one, isn't it? This will be equal to that, right? This will be equal to that. And this will be equal to this, isn't it? So in that case, it will have only 6 values. The same thing if you have it in 2D. Because this is in 3D. In 2D, it will just be kxx, xy, yy, no, yx, yy in 2D, right? So this is what is called a tensor. Okay? And for isometric aquifer, kx, ky, kz equals k. Simple, isn't it? But for anisometric porous media, no. Kx is not equal to ky and is not equal to kz. So it will have different values at a single point. Although later we are going to see that in practice, soils are anisotropic. But like I say, for simplicity, instead of having 9 values, or even 6 values, or just 3 values, we say that the aquifer is isotropic. Okay? Because more often than not, we take the kx, or the resultant horizontal hydraulic conductivity. It's not just kx, because here is a plane, right? You have, let's say, yx, and then the vertical one is the z-axis, isn't it? So if you have two components here, you also have a resultant horizontal component, isn't it? So that resultant horizontal component of the hydraulic conductivity is several orders of magnitude higher than the vertical component. Is that clear? So that's why for practical purposes, we consider only the horizontal component and assume that the aquifer is isotropic. But still, in that case, we can have still some anisotropic aquifers. Okay? Yes.
Now, this matrix.
Yes.
You said when they are aligned.
Yes.
Then we are going to have three values.
Yes. This will be 0 and we'll only have, yes.
Now, if they are not aligned.
Yes, then we'll have 9 values, or basically 6 values.
And that's where my confusion.
In practice, because when doing the matrix operation, it will still be like this, but this one will be equal to this will be equal to that, and this will be equal to this, because it is symmetric. Is that clear? So it's going to be 9, but in actual sense, it will be 6. Yeah. If it is not aligned. Yeah. But for simplicity, we all put this in our assumption. That's for anisotropic aquifer. We say, okay, the principal directions are aligned with the coordinate axis. And for that, you will only have the 3 values of the hydraulic conductivity. He is sleeping. Are you sleeping? Oh, are you tired? Not well? Huh? But you don't know where your notes are or what? Oh. Then in that case, you can pick any good book in fluid mechanics, which would have, let's say, summarized everything. What?
Rajput.
Pardon? Rajput. I don't know. But for me, probably, I will suggest there is one fluid mechanics by Crow and some other authors. Crow et al. I don't remember the other authors. Okay. For Rajput, I'm not aware of that one. All right. So is that clear? Okay. So now we understood what is homogeneity, isotropic, so that when I mention that the aquifer is homogeneous, isotropic, all the meanings should come back to, okay, by homogeneous it means this, by isotropic it means that. Okay? Now, I think that is that about the hydraulic conductivity. The hydraulic conductivity. No, that is not, we are not yet through with it. This is just about treating it as a tensor. It is just about treating the hydraulic conductivity as a tensor. Now we will move on to what is hydraulic conductivity? Yes. What is hydraulic conductivity? Can you tell me? Yes. What is hydraulic conductivity? What? Write it first, okay. I'm waiting, although my time is up. And I think you will have another lecture now, right? At 10. You will have another lecture, right? Huh? Yeah, Dr. Ajibike just told me that he will have a class at 10. So, have you written it down? Okay.
Is the flow in liter per
Oh, you want to give me some matter? Okay, go ahead. Is the flow in what?
Is the flow in meter cube per second?
Meter cube per second.
Liters per second?
Liters per second.
That's a medium.
When defining a term, it's better you define it in terms of dimension. The dimension of hydraulic conductivity is, maybe you see L, you thought it's liter. This is dimension for length. So it has unit of velocity. If you say meter per second, it's a unit of.
I want to relate it to the Darcy's equation.
With whatever you relate it with, this is the unit. Okay? So it's not liters per second. But I'm sure probably you see L over T. So you misinterpreted L to be liter. No, it's not liter. It's length. It is defined using dimensions. It's better you define terms using dimensions, because the unit can change at any. You can have meter, you can have kilometer, you can have centimeter. But if you use the dimension, it represents all the range of units under that physical quantity. Okay? So now in practice, just tell me, what is hydraulic conductivity?
The rate at which water passes through a soil medium.
The ease, not the rate. The ease. The ease with which water passes through the voids. That is defined as hydraulic conductivity. Okay? So
What about transmissivity?
we are coming to that. Don't worry. Yeah. We are coming to transmissivity. Okay? Now we are on hydraulic conductivity. Later we will explain transmissivity. So it is the ease with which water passes through a porous media. Okay? Transmissivity is also the ease with which water passes through the entire breadth, entire B. B is the depth, isn't it? It's the width, entire width of the aquifer, and it's related with hydraulic conductivity. But that, like I said, we will have something on that, because we may need to expatiate on the transmissivity, but that will be later. Now, you will agree with me that the hydraulic conductivity will depend on some factors, right? It is the ease with which water or fluid passes through the porous media. So what is it going to depend on? What do you think that the hydraulic conductivity depends on? What? One at a time? Voids. And what else?
Soil testing.
What?
Soil testing.
Soil.
The grain arrangement.
Because the bigger the grain, the more the bone space. Soil testing.
Texture. Okay. Okay. Yes. Any other thing?
Soil compactness.
Soil compactness. Yes. Any other thing?
Soil aggregate.
You are just mentioning the properties of the porous media now, isn't it? Which I agree with you.
Cross-sectional area.
Well, what about the property of the fluid itself? Will it affect the rate the ease with which it passes through those voids?
Yes.
Then why didn't you mention any of the properties of the fluid itself? Density. Yeah, although more often than not we assume that it has constant density. Although in practice, the density could change, most especially for groundwater, which is usually more or highly mineralized. It has dissolved ions. Okay? So the density could change, right? But by the way, when you have pure water, was it in this class I explained deionized water? No, it wasn't, right? Okay, when you have distilled water and groundwater, which one will have higher density? Groundwater? Are you sure? Sure? Why?
Because it has
Impurities? So due to the impurities, the density will increase? So the density will increase, right? Okay. So the density here, we usually assume it to be constant, okay? But although sometimes, most especially for groundwater, the density could change, most especially for confined aquifer. Because sometimes, I explained about the effective stress and total stress, and how these vary when you are taking water out of a confined aquifer, which we mentioned, the pressure could change, but the volume of water essentially doesn't change. And that is due to the interaction, because the aquifer grains tend to compact, because they have compressibility factor. So when you're taking water out of a confined aquifer, the pressure could drop, but then the amount of water remains the same due to the fact that the aquifer grains are compacting. When they compact, they expel more water. They compact and now push more water out. And that will now take care of the amount of water within the aquifer. And also the density, as we are going to see, but that will be in the other class when we are looking at solid transport. When deriving the equation for advection, we will look at the change in pressure resulting, not the elastic change occurring as a result of change in density, rather than change in the compressibility of the aquifer grains. But that we will explain later. Okay? But then, what was I even explaining that I came to this? Okay, we are explaining about the properties, thus affecting the hydraulic conductivity. You mentioned a lot about the properties of the porous media affecting hydraulic conductivity. Now I was asking you about the properties of the fluid affecting hydraulic conductivity. You mentioned density. 1, 2. Viscosity. What else? Okay. So this goes to tell you that the hydraulic conductivity is made up of 2 things, isn't it? 2 things in which the first one, let's say, is a property of the porous media, right? The second one, properties of the fluid itself, isn't it? And that's why it is defined as, you have this is small k, this capital K. The hydraulic conductivity is written out using capital K, but you have small k, subscript I, called intrinsic permeability into rho g over mu. The intrinsic permeability, in some texts they call it permeability, okay? But more often than not, permeability and hydraulic conductivity are synonymous, okay? So when I say hydraulic conductivity, I mean permeability. But in some texts, they refer to intrinsic permeability as just permeability, okay? So this is called intrinsic permeability, which gives, or which depends on the shape of the soil grains and the void space. Okay, so taking care of the properties of the porous media, isn't it? While this is unit weight of water, isn't it? Unit weight, rho g over mu. Taking care of the properties of the fluid itself. Are you following? For chemical engineers, the intrinsic permeability is most important to them. Okay? Because they're exploring oil, so they use the intrinsic permeability more. For hydrogeologists and water engineers, we use the hydraulic conductivity more. Is that clear? But because Ki is usually given with a coefficient CD square, where D is the diameter of the aquifer grains and what have you. And C is another complex mathematical expression, which takes care of the properties of the porous media. Okay? And the dimension, the unit is L over T. It has a unit of velocity. Okay? It has a unit of velocity. And we mentioned that it's a scalar quantity, but a tensor, isn't it? Second rank tensor. What else? For now, we'll stop here. And then in our next class, we will move on to, you see, we have explained the hydraulic gradient. Now we move to the hydraulic conductivity. And then we'll move to the area. And then we'll move to Darcy velocity and seepage velocity. And then from there, we move on. Okay? So any question? Yes.
Determine the intrinsic permeability is independent of the properties of the fluid.
Yes. The intrinsic permeability, yes. It represents only the properties of the porous media. Okay? But it's part of the hydraulic conductivity, which is now the one that combines all properties of the porous media and that of the fluid. But intrinsic permeability refers only to the properties of the porous media. Yes?
You said you are going to explain why flow rate is a scalar quantity.
No, but we haven't. We are just even explaining this one, the hydraulic conductivity. We are moving from hydraulic gradient, now hydraulic conductivity. We'll move to the area. And then we'll move to seepage velocity and Darcy velocity, and then to the discharge. Okay, so just cool down. We still have so many classes to cover this. Okay? Any question? All right. So see you next week on Thursday at 8 or 9. Okay. So at 8.